So today's going to be the last lecture for this week, and then on Friday, your final project is due, and it will also be a work session. So if you have any questions, any like last minute concerns, you can come in during normal class time to the Zoom channel and ask me those questions, or just, come in, hang out, and work on the final touches for your project. Today we're going to talk about dead zones or low oxygen zones. I have a really short lecture today, a somewhat lengthy activity for you to do, and then I'm going to leave some time at the end of class for you to do student evaluations. Can you guys hear me? Okay, sweet. Thank you. Oh, and thank you for all of you that rated me on Rate My Professor. It was really nice to read those. It definitely was the highlight of my week, so I really appreciate that. I've really enjoyed this class a lot. I feel really lucky that we all got to be in class together this semester, because you all have been really great students for me, and hopefully you've learned a lot about the Gulf of Mexico and enjoyed the course. It sounds like you did, so that's great. That's my goal. So today we're going to talk about hypoxia, what it is, what causes it in coastal areas. We'll talk about impacts of hypoxia on fish and other organisms. We'll talk about the Gulf of Mexico dead zone, and then the activity is on the Mobile Bay Jubilee, which is a phenomenon that you may or may not be familiar with, but you will be after this class, and it's kind of cool. Aw, thanks, Anton. I appreciate that. I really do. I enjoy teaching you guys. Just to let you know, I'm going to be showing you pictures from my own research in this PowerPoint. I do some research on hypoxia in the Gulf of Mexico. Most of my job is a research appointment. I only teach this class. I only teach 2 classes throughout the year. So most of my time is spent doing research. And one of my jobs is to go out on big research cruises to understand coastal hypoxia in the Gulf of Mexico. So this is actually me in this picture from this past summer on the hypoxia cruise, which I will tell you about later. So the learning goals for today are to understand that the supply of nutrients, especially nitrate, to surface waters impacts levels of dissolved oxygen all the way down near the seafloor. You'll learn the area of temporary hypoxic bottom water that occurs most summers off the coast of Louisiana. In the Gulf of Mexico is the largest of its kind in the United States, and it's actually the second largest in the world. And you'll learn about Jubilee events and how, even though they may occur in other areas of the world, Mobile Bay is probably the only place on Earth where these occur every single year. Super weird events. I've got a whole activity for you on them. I think you'll like it. Okay. So what is a coastal dead zone? A dead zone is an area of an ocean, or it could be a lake, but we're usually talking about oceans in this class, that has too little oxygen to support marine life. And that means it's hypoxic. And so hypoxia is where there is too little oxygen to support marine life. Dead zones are actually a natural phenomenon that occurred before human settlement in many regions of the world, but the problem has been increasing, where hypoxic zones are popping up in areas where they never were before, or pre-existing hypoxic zones are getting way worse, and they've been increasing as a result of human activities. This image here is showing you the size and number of marine dead zones in the world that are known. We're discovering new ones all the time. So these tend to be areas that are really highly studied, and so that's why we know there are so many dead zones here. Probably there are quite a few more that we're missing in areas that are less well studied. Let's talk about some of the causes. So there are a number of reasons that these dead zones form. The first cause, probably the most important, is eutrophication. And this is where the supply of nutrients at the surface impacts the level of dissolved oxygen at the seafloor. This is because, we talked about eutrophication in the last lecture. We didn't really talk very much about how it impacts bottom dissolved oxygen, but I think that this makes sense from what you've learned. So nutrients will feed the algae and cause it to bloom, and then there are not enough critters to eat up all of that algae, and so a lot of that bloom will die, sink to the bottom, and decompose. And the process of decomposition is essentially just bacteria feeding on organic matter. You get blooms of bacteria that occur. And those bacteria, as they're feeding, they need to be doing respiration, which means they're using up the available oxygen. So this decreases the oxygen in the water column and lowers the dissolved oxygen level even at the bottom. The second cause has to do with the ability of the water column to mix, and so its ability to flush out those low dissolved oxygen levels and deliver new oxygen to the deeper areas of the water column. There are a number of reasons that you'd have water column mixing to kind of get rid of the hypoxia. You could have, for instance, changes in the amount of river flow, changes in winds, and changes in tides. All of these can strengthen or weaken water column stratification, which can affect the oxygen exchange. And stratification is when water masses, specific layers of water, don't mix because they have different properties, different densities. There's a pycnocline there. We talked about pycnoclines earlier in this class, and that's where you have two bodies of water with different density qualities, and they resist mixing. When that happens, the water becomes stratified, and one of the things that doesn't get mixed is oxygen. And so this is an image here that shows you an area where a pycnocline is formed, and you get oxygen at the surface here from all of this phytoplankton that's blooming, but that oxygen doesn't make its way down below the pycnocline. What does make it below the pycnocline is a whole bunch of dead phytoplankton and fuel these bacteria blooms, which eat up all of the available oxygen. This image here is showing you an example of what can happen when mixing does occur through extreme tidal activity. This is from the Medallion hypoxic zone, which is part of the Pearl River Delta, which of course we learned about earlier in the class as one of the China's premier regions for economic growth. So this is a location that has lots of cities around it. And typically you get this tongue of the blue and green water here, which indicates low dissolved oxygen water. And this is during a not very extreme tidal stage, a neap tide. But when you have some extreme tides coming in, more water rushing in, more water rushing out during a spring tide, you get that low dissolved oxygen area disappearing in the estuary. And a lot of areas are oxygenated once again. So tidal activity can mix these areas and at least temporarily get rid of the hypoxic zone, though oftentimes, as soon as these spring tides are done, that hypoxic zone will come right back. But at least it gives the critters a little break. Cause number 3, global ocean deoxygenation. This one's kind of scary. Scares me anyways. The open ocean is estimated to have lost about 2% of its oxygen over the past 50 years. And this has resulted in an expansion of something called oxygen minimum zones, which are known as OMZs. Over the past 50 years, the total area of oxygen minimum zones has expanded by about the equivalent of half of the area of Canada. And these oxygen minimum zones are shown here in these blue areas. They're open ocean zones, so these aren't necessarily coastal areas. And these zones occur in the middle of the water column, and that's where the hypoxia occurs. I taught extensively about why this hypoxia happens in my Intro to Oceanography course, and unfortunately I don't have a lot of time to review why these OMZs appear and why they strengthen, but if you are interested and you don't remember from Intro to Oceanography, I can give you those slides. Normally I would do a review here, but we're short on time today, so. Suffice to say, they exist, they're in the middle of the water column, and they're in the open ocean. There are two main causes for falling oxygen content in the open ocean. Both are related to climate warming. First of all, as the ocean warms, less oxygen can be held in the water, so less oxygen dissolves in the water. Cold water holds more oxygen. So warming water has less oxygen in it already. So that's responsible for some of it. But most of it is because of enhanced stratification from ocean warming. So as the surface waters warm, they become less dense, and that enhances any sort of pycnocline that's there. It'll strengthen it, and it'll decrease the amount of oxygen that's mixed to deeper levels. So typically just below that picnic line is where you end up getting a oxygen minimum zone. This low oxygen ocean water, even though it happens in the open ocean, it can contribute to the problem of coastal hypoxia, because the water that's flushing through the system due to tidal activity is already depleted in oxygen. So for instance, here in these estuaries in India, you can imagine that any sort of tidal activity that's bringing water into these estuaries is not providing much relief because it's already extremely low in dissolved oxygen. And there's one more cause for coastal hypoxia. You can see a lot of these kind of work together, and a lot of these are due to climate change or changing land use practices. The fourth cause is upwelling. A poster child for hypoxia that's related to upwelling is Oregon. In the summer of 2002, there was a brand new coastal hypoxic zone forming in Oregon for the first time. It surprised a lot of people, killed a lot of marine animals, including a very important Dungeness crab fishery there. Fishery still exists, but now they have to contend with coastal hypoxia that recurs every single summer since 2002. In this case, there isn't a whole lot of fertilizers that make their way into the water in coastal Oregon. Nobody lives in Oregon. Okay, a couple people did. A couple people live in Oregon, but it's relatively wild. There really aren't that many people there. So in this case, hypoxic events are linked to shifts in upwelling. Upwelling is a process where deep, cold water rises towards the surface, and what you end up getting is cold, salty, nutrient-rich, generally low oxygen water from the OMZ, moving up onto the continental shelf and into shallower and shallower waters. The reason for this happening is, of course, due to climate change. So changes brought about by changing climate have strengthened the northerly winds, making them happen more often for longer periods of time and strengthening those northerly winds. Because of the Coriolis effect, the net movement of water is offshore in these shelf areas. And so as this water is moving offshore, something has to come in to take its place. And what comes in to take its place is water from deeper areas. And so you get this low dissolved oxygen, high nutrient water, upwelling up to take its place. Because there are a lot of nutrients in this water, you can also get a little bit of eutrophication happening. This isn't necessarily eutrophication from fertilizers. Instead, it's eutrophication that's more natural. Okay, so we talked about why hypoxia happens. Let's talk about why it's a problem. So fish can tolerate a certain amount of low dissolved oxygen. As the dissolved oxygen decreases from somewhere around 7 to 10 parts per million, once it decreases below that, fish start to have some issues. The first thing that happens is activity might fall off a little bit, or growth rates might fall off a little bit, and that happens for some fish at levels below about 7. At about 6, you stop getting spawning activity happening in some fish. And then when you get down to about 4, you start to have some severe issues. And this is typically the cutoff for hypoxia. So this wedge right here kind of shows you more of what happens once you get below 4. 3 to 4, you start to have avoidance of the area by some fish. At around 2, you get no fish present at all. You really won't see anything in these areas in terms of fish life. At around 1.5, you start to see shrimp and crabs disappear. At 1, you get a whole bunch of animals that couldn't escape, are laying on the surface trying to get some dissolved oxygen. They come out of their burrows and they lay on the surface of the sediment. And you start to get even the most tolerant animals in terms of dissolved oxygen start to die off. And then at 0.5, you get formation of microbial mats. So really only bacteria are forming. They're blooming to eat up anything that died in the hypoxic zone. And your sediment geochemistry and basic processes of the ecosystem fail as you approach 0. 0 is known as anoxia. There's no oxygen there. The rest of this, from 0 to 4, is known as hypoxia. So that leads us to our own dead zone off of our coast. This is where it's located. So this is the Mississippi River Delta. And our dead zone is off the coast of Louisiana, pretty much stretching the entire coast of Louisiana and into Texas a little bit. So if you were to drive directly south and go offshore, you would eventually, if you were in the summer, you would make it into the dead zone. Does Subnautica have a dead zone? I haven't played it yet. You're talking about the game, right? Yeah, I really want to play it, but I kind of want to play it in VR. Because that sounds pretty awesome. Is it terrible? Okay, that's good to know. That's good to know. I won't wait then. That's pretty funny. I do want to play it though. It's definitely like right up my alley. Okay, that's good to know. Well, maybe this summer, maybe after this class is over, I'll buy Subnautica for myself and enjoy it. Okay, well anyways, let's talk about the non-Subnautica dead zone, the one that exists off our coast. This is an area of temporary hypoxic bottom water, so below 4 parts per million, that occurs most summers off the coast of Louisiana in the Gulf of Mexico. And it's the largest recurring hypoxic zone in the United States and the second largest in the world. The cause of this hypoxic zone is eutrophication and stratification. These are the main causes. We don't really get upwelling in this area, and we don't really have to contend with a big zone of deoxygenated OMZ water, and so eutrophication and stratification are our main causes. And for that reason, this zone only occurs in the summer, because in the summer we have warming, which increases stratification. We have fewer storms, though, I mean, you wouldn't know it from the past couple of days, but typically we have fewer storms in the summer, so there's low amounts of wind-driven mixing. And we have high amounts of nutrient addition in the spring that allow fertilizers to enter the Gulf of Mexico and fuel these massive phytoplankton blooms every spring. And so in summer we have to contend with all of that phytoplankton that died and sunk to the bottom and are causing this dead zone. There's been a great time series since 1985 that tracks the size of the dead zone each summer. This was actually the size of the dead zone in 2019. It was quite large that year. And so let's see, this is 2020 and 2019 was right here. So it was above the 5-year average. We have a goal for the hypoxic zone that's actually like way down here. We almost never reach our goal, and that goal would be achieved by decreasing the amount of fertilizers that make their way into the Mississippi River. But there are a lot of states that are involved in this and a lot of people's livelihoods, and it's a really, really, really difficult issue, as you can imagine. So if you recall, a few weeks ago, I had Dr. Nancy Rabelais sit in on my class to give me some feedback on my teaching. And I told you that she was responsible for our understanding of the dead zone in the Gulf of Mexico. So I wanted to talk a little bit about 2 LSU scientists, Dr. Nancy Rabelais, who's pictured up here, and Dr. Eugene Turner right here, who discovered the Gulf of Mexico dead zone in the 1970s. And they determined it was an annual summer event at that time. Both of these professors are still at LSU, so they're still working, and I thought it would be good for you to know that a lot of your teachers, these 2 still teach classes, a lot of your teachers are responsible for some of the major discoveries in the region in terms of whatever their field may be. So you've got a lot of really, really good researchers teaching you, and so I wanted to reiterate that point. So these two are still around. In the 1970s, they discovered this hypoxic zone and they wanted to figure out its cause, and within a few years, they were able to track down its principal source, being chemical fertilizer from the Mississippi River drainage basin. So all the fertilizer that's used in the entire Mississippi River basin ends up making its way into the Gulf of Mexico and feeding this dead zone. In the 21st century, scientists saw a spike in fertilizer use and the size of the dead zone increased. And so they were able to kind of, unfortunately, test this idea that the dead zone was caused by fertilizers because use increased, and so the dead zone did as well. So every year, as I mentioned, we go out on this hypoxia cruise to map the area of hypoxic bottom water. And last year, I was in charge of the hypoxia cruise. This is my science team right here, and I'm standing right here in the middle. When we go out, we visit the same locations every year. We'll go out and track the size of the dead zone, make sure we get to like visualize where its different edges are. And the way that we do that is by dropping this instrument called a CTD over the side of the boat. It stands for conductivity, temperature, depth. But it's basically an instrument that has a whole bunch of things on it. So it's got on the bottom here, you can barely see all these little black devices. Those are all sensors. And then what you mainly see is this ring of what we call Niskin bottles, which are just bottles that are used to collect water that we can trigger at different times when we want to collect a water sample. And so this device is lowered through the water column. This is me trying to get it off the boat. It's very heavy, as you can imagine. And this is my PhD student, Jill. The sensors at the bottom of the CTD record depth, temperature, salinity, dissolved oxygen, and others. This is a picture of the panel in the control room that's tracking the CTD as it goes through the water column. And on this picture, these purple lines are the dissolved oxygen. So you can see throughout the top of the water column, we get a lot of dissolved oxygen. Then we reach an area that has stratification and that dissolved oxygen drops quickly. And then we get values that are really harmful for life. In this station, these values were around 1. So we wouldn't have expected any life to be present there, near the bottom. And then the Niskin bottles get triggered to collect water samples. So I'll be in the control room while this thing is being lowered. This is me and my student Jill. And I'll be telling the Niskin bottles when to fire so we can collect some water samples and bring them on board. And we use these water samples to understand the nutrients that are present in the water, as well as to double check the dissolved oxygen levels that are being read by the sensors, so our sensors aren't lying to us. And this is my student Jill in the lab doing some work to determine the dissolved oxygen levels using titration, so we can figure out if the sensors are working properly. The lab's right on the boat, so we're out there for anywhere between 10 days and 2 weeks to visit all these stations, do all this lab work. We sleep on the boat. The boat has, in addition to its science crew, it has 2 captains, so it can run all night. We sample all night. We have a day and a night crew. And a variety of people that keep the boat going, and it has its own chef, and the food is fantastic. It's really good. I don't think I ate so well in the past 2 years as I did on this boat. So this is run out of Lumcon. How much oxygen is present in areas you'd think of as the deep sea, where all the weird things are, and it's all dark. There's actually quite a bit of oxygen down there. It's not considered hypoxic in the deep sea because there are deep sea currents. So the difference is that in these oxygen minimum zones that are somewhere in the middle of the water column, we end up getting stratification that prevents currents from forming. So you get surface currents and you get deep currents, but you don't have anything mixing the two. So those deep currents can still deliver oxygen to areas in the deep sea, and they definitely do that. You also don't have, it's cold down there, right? So you don't have as many things using up the oxygen as quickly. So that's important. As the deep sea warms, which we do expect it to do in time, we might expect more oxygen demand there, and so we might see some hypoxic areas form down there. Do you really? I've always wondered who lives in those camps. That's super cool. I wonder if any of them are on Airbnb, because I think it would be really fun to stay in some of those buildings on stilts that are right across from LumCon. So you've seen those big boats then? Yep. So the one that we go out for this cruise is the largest one, the Pelican. Last year when I went out, we actually found that the dead zone was smaller than expected. That's because a hurricane had just passed through. In fact, we were on the water pretty much immediately after the hurricane passed through, and we had to contend with 10 to 12 foot waves our first night, which was real fun. There was like stuff flying everywhere, and I kept thinking I was going to roll out of bed, but I didn't. I didn't even injure myself, which is pretty good because I was still getting my sea legs. But anyways, the hurricane that passed through mixed the water column and reduced the hypoxic zone size. And so you can see here that the red areas, which were the worst areas of hypoxia, were actually quite small and fragmented, and the areas with a decent amount of oxygen, these yellow areas, they encompassed most of this zone. So that was an interesting finding from last year. Again, once that stratification breaks down, the oxygen starts to be delivered to the bottom, so you get that hypoxia breakdown. So that was today's lecture on hypoxia. Now I want you to go ahead and do the activity that I have on Jubilee events in Mobile Bay, which are another example of an impact of low dissolved oxygen in the Gulf of Mexico. Once you're done with that activity, I ask you to please go and spend some time doing student evaluations that are located through your My LSU page. So there should be a link on the left-hand side for student evaluations, and they should be open now. Please take some time to evaluate my class. So what happens is, in a couple years, I'm going to be going up for tenure, and they'll decide whether or not they want to keep me around. And the only way they judge my teaching is through your student evaluations, specifically the numbers that you rate me. So I need a lot of people to evaluate me, so that way they can have a really good idea of how I am as a teacher. So please do those evaluations. I would really appreciate it. It's your way of ensuring that I stick around if that's something that you think would be good for the university. Okay, that's the end of class. So we'll go ahead and call it there, but I'm going to keep this activity actually open until tomorrow because I know a bunch of people couldn't make it to class today because they don't have power. So I'll keep it open till tomorrow so you have plenty of time to continue on if you want to learn more about Jubilees. They're super weird, aren't they? Remember the first time I learned about Jubilees, I was like, really? This happens every year? Very cool cultural thing about the area. So something I thought you should know about. So Friday's going to be a work session. If you don't come to the work session, which of course is optional, have a wonderful weekend, and I will see you on Monday for one of our last couple of lectures.